So a chicken lays n eggs. Each egg is laid independently, and it does or does not hatch with probability p of hatching. For each egg that hatches, the chicken does or does not survive independently. That is happening with probability s. We're letting n be distributed binomial with the parameters n and p, and that's the number of eggs. X be the number of chickens which survive, and Y be the number of chicks which hatch but do not survive. So X plus Y are basically n. We are first asked to find the marginal of PMF of X, and then the joint of PMF of X and Y. And then we are asked also if X and Y are independent. So I'm actually going to start with the PMF of X and Y, and then do the marginal of X. Okay, so first of all, we know that hatching is given. Hatching is given with probability p, and survival is given with probability s, and we also know that n is distributed binomial and p, and then we know that x plus y are equal to n. All right, so let's start with the finding the PMF of x and y. So the easiest here is obviously sort of we know that there are 3 random variables in the system. That is to marginalize over the joint of x, y, and n, and we're going to marginalize over n, so all cases of n, and that is from 0 to n. We also know that this this joint, we can condition on n, so by base rule. So let's write that out. So we have I from 0 to little n, because we know that there are n chicks, but we're going to now do the marginal x, y, conditional on n is the same as x plus y, n equal x plus y. So this we know. We also know that this marginal of n is a binomial, and we also know that conditioning on n, we know that these things are basically, it's the same event, right? It's either, we get x chicks survive, or y of them hatch but don't survive. So it's basically the same thing. So we can basically choose to drop one. We're going to drop y, and this we can do when we know by conditioning on the event of x and y. Now, there's also another thing that, I've wrote out this whole sum here, but actually, what is happening, it's a subtle but important thing, is that this joint of x and y, it's actually, choosing a fixed number, here. So x, little x is actually, a, and y is, say, b. So it means that this sum is only has a probability that is different from 0 for only the cases where I equals a plus b. So essentially it means that this will revert to only one case where that is true, and the rest are 0 if we write out this full sum. And so in the end, what we have is the probability of x equal a, and I'm dropping well, for the sake of completeness, let's just write out y here equaling b. Then we have n that has to equal a plus b. So basically that happens only in that occasion, whatever we choose for little x, little y. The same here, n equal a plus b. Okay, and now because it's the same event, I'm going to drop, it's superfluous to write out y here. So we're going to write probability of event x equaling little a, conditioning on n equal a plus b, probability of n equal a plus b. And as I just said here, before the conditioning on n, we know that x has to be binomial. So that's binomial and this is binomial. And so writing out this probability, we know that conditioning on, so we have a plus b units, and we're going to select a that survive, and that survival probability is a, not surviving is 1 minus s, so s is the probability of survival, a units, and then we have the rest of those units not surviving, so that's a plus b minus a, so basically b, multiplied by this marginal of n, and that we know is binomial. That we know that we have n x, so that's a, so we choose n, from n we choose a plus b, and the probability of hatching now is p a plus b, and not hatching is a plus a minus b, n minus a plus b, like so. Okay, and this is basically the joint of x and y, and we can actually move on and simplify this further. And there's another realization here, and that realization is that this whole term here ends up being a multinomial if we also encode the eggs that do not hatch. And so we'll basically have three categories: those that hatch and survive, those that hatch don't survive, and those that hatch and those that do not hatch at all. Okay, so we have three categories disjunct. And so let's just open up these. So they have a plus b, choose a plus b minus a. Just going to show this multinomial probability. I think that's a nice realization. We have the s a and minus s, and then we have the b, we have it n factorial, and we have a plus b factorial, we have n minus a plus b factorial, and then we have a p a plus b. Oops, that was a little off. 1 minus b, n minus a minus b, like so. Now we're going to see that we can, these two cancel. And let's just collect all the factorial terms. So we have n factorial. What we have left is a factorial, b factorial. The b factorial is coming from what remains in here. And we have the n minus a minus b factorial. Okay, so, and then we have the s p power a, so we have the s and a, and then we have a p and a here. So you're going to collect all these probabilities, and then we have the p times 1 minus s, the b, so that's what remains from here with that. And the remainder is the 1 minus p, n minus a minus b. And so what we have here is those that hatch and survive, a of them. These are the a's here, so we're basically taking the factorial of those. We have all combinations here. And these are the ones that didn't survive, hatch and didn't survive, b of them. And then we have all of them that didn't hatch, and these are the ones that remain basically here. Like so. Okay, so that's nice. And actually, just one important note here is that are these independent? And they are. X and Y, are they independent? Well, actually, compared to the chicken and egg problem, the real one where these are Poisson, here they are, X and Y are not independent, and that occurs because we have the constraints of that the X and the Y has to be less than or equal to n. So basically, you know, Y, if we know, because we know X already, we know n, that's fixed, right? It's given here, it never changes. If we know X, we will have information about Y. So the critical part compared to the original chicken and egg problem is that n is also chosen chosen randomly, and that's chosen from a Poisson. Okay, so let's move to the second part of the problem, and that is to find the marginal of the PMF of X. Okay, so that we can do in two ways. One is the easiest, which is just a story proof, and then the other one, which is just algebraically showing the same thing. The algebraic proof is a little longer, and so I'm going to show it. But let me just start with the story proof. So let's just make some space here. And the story proof is basically that we know the two stages are independent. So we have with probability P that a egg hatches, and we also know with probability S that the chick survives, and we know that that happens from n eggs. So it must be that X is distributed binomial, chosen from n with probability S and P. So that's a pretty simple sort of proof. Because these two stages are independent, we can just basically multiply them together, and n is fixed. So what we end up is this X distributed binomial. Let's show this by algebraically. So the marginal of P of X we take the, that was an ugly sum. We take it over the joins of X and n. And we're doing n because we know we know that n is given for us. We know that n is binomial, and that would simplify our lives immensely by conditioning on what we know. And so this term here we can write or rewrite as the n of j, p of n equaling j. Okay, and the sum here goes from I starting at x up to n. And why are we doing it over, why is this not equal to 0? Well, it's because that j has to be equal or larger than x, because it is constrained by the fact that we are choosing x here first. So for all other terms, the sum is summing just 0 probabilities. Okay, and there's another fact that comes from the previous exercise that we solved, that this x here is actually, we're choosing that as well. That's what sort of it means by x being setting sort of the floor for j. So we are actually in fact saying that x is a number I. It's not for all x's. It's x that we select. And so in fact, it's easier if we want to write x here equaling I, if we wanted to. And so, but I'm just going to keep x for now to simplify things. In terms of notation, I and j is going to be a little close to each other in terms of just visual. So let's keep that and write out now what we know. So we have the sum over j equal x up to n. We know that the conditional has to be binomial, condition on n, and then we select the number of chicks that actually survive. So what we have now is we have a j. We know that for j, x survives, and then survival probability is s. That's over x. We have 1 minus s j minus x that don't survive, and then we're multiplying that by the marginal of n, and that has to be n, selecting over j. So n is given for us. We know that n is the number of eggs, and p of them hatch, and so j of them will hatch. The 1 minus p of them and minus j won't hatch. Okay, and so this whole thing here, by the story proof, we know has to be simplifying to a binomial NSP. And what is that? That is, let's write it down here. I'm going to put a question mark, asking in fact if this can be simplified to it. So it's n x, and then we have sp of x, 1 minus p, sp, and minus x. That is the binomial distribution for x as said by proven by the story proof. So the question is, algebraically, if we can prove this once again, but from another strategy. So let's start by writing out this. Just basically writing out these businesses here. So that's a j factorial. We have x factorial j minus x factorial, s and x. We have the 1 minus s j. That's an s j minus x, and factorial j factorial n minus j factorial, pj, 1 minus p, n minus j. And we have the sum over this whole thing here, j to x to n. All right, so here we can immediately see that and that should be a j factorial, that this term starts, and that simplifies, and we have terms that don't depend on j. We have the s of x, we have other terms, we have the p factor, n factorial, sorry, and we have yeah, we have those terms for now. So let's collect terms. So we have the n factorial, and we have the x factorial. So we have just pulled out this term, that term, we have the sx, that is this term. So now there's just a bunch of housekeeping, making sure that we don't miss any terms. And then we have the sum. I need to write the sum over here, j x over n. And what we have is 1 j minus x factorial and the n minus j factorial. Okay, we have the probability p, j. We have the 1 minus p, n minus j. Okay, I don't think I've missed any. Well, we have the 1 minus of this term here as well. Let's write it here. Well, actually, just to keep things in order, I'm going to put it to the left here. 1 minus s, j minus x, like so. Okay, we have those three terms. So now what we're going to do, we're going to this sum, I'm going to change variable, just because this is a little disturbing, j equaling x, a little hard to work with. So what we're going to do is that we're going to write the following sum. So we'll have a sum, I'm going to start at 0, so we'll have to subtract off x both sides of this sum, like so, and we're going to set this thing to r. So r, as a side note, r is going to be j minus x. And so j is, the index of interest is r plus x equaling j, like so. All right, let's create some more space. So have some more housekeeping to do, and so let's copy this, put it here. Okay, so we have the sum, r equal 0, n minus x. Okay, and so we have this term. Well, so this term is going to be r. This term here is going to be r plus x, and this term here is going to be r plus x. This is also r plus x, and that's going to be r plus x as well. Okay, let's see what we end up with here, and we will have some more terms that we can liberate from this sum. And so we have r factorial, we have n minus r plus x factorial. Then we have the 1 minus s r to the plus minus x. So we have plus x. So we'll have just one r there. And then we have the p to the r plus x. 1 minus p n minus r minus x. Okay. So let's pull out some terms here. And the next round, like so. Okay, so we have into the let's see, what do we have? We have the following. So let's say green. So this is just r, right? We're going to be able to pull out the p and an x. We're going to be able to pull out a 1 minus p n minus x here. Okay, so let's now write the p of x, right? And we have the 1 minus p, 1 minus p on the n minus x. Okay, right? So we have then just got rid of this. There's a lot of housekeeping here, and this and that, and this is just an r. Okay. And now there's another thing. What we're going to do here, we're going to, because this looks awfully close to a choose x. So n minus x, like so. But then I'm going to write another one here, n minus x, because this looks awfully close to that in here as well. But we have n, from n minus x, we're going to choose r, because we have an n and an x here. Okay, so this is then now n choose x, sp x. See that we're getting close to binomial form. 1 minus p, 1 minus p n minus x. And then we have the sum. We have the sum, which is r equal 0, n minus x. And this is in fact a n minus x choose r, right? And what we have here, we end up with, let's see, what do we have here? So this whole thing that is left is 1 minus s r p r 1 minus p minus r. So this whole thing is writing it into the same parentheses. So we have 1 minus s p 1 minus p to the r. Okay. Now there's another thing we can do. Imagine that we have a 1 times, so we have a 1 obviously there, and that we can do a lot, because if we had this, we can utilize the binomial theorem, and I can do, I can do anything here, which is n, can do an n minus I minus r. Sorry, I meant x. Why? Well, because n minus x we have here, and we have minus r, which is the choose. So this is basically now ripe for a binomial theorem, which means that this whole thing is just 1 coming from this one plus this whole term here, which is that 1 s p to the p 1 minus p to the r, like so. Sorry, not to the r, to the n minus x. This is just by the binomial theorem. All right, so this, now we got rid of the sum, and we are basically almost there now. And we'll see that this, and I'm going to write the nx sp to the x. We can see that we can write this and that under the same parentheses. And so let's do that. Let's just continue. Let's see. We can write it. Let's write it. Well, 1 minus p to the well, let's do the following. I have the 1 minus p. I'm going to pull it in to the parentheses, so we have a 1 plus, and this whole business there. Actually, I'm going to do it here to the right. So let's move this whole thing. I'm going to move in here. I'm going to give it another color. Let's give it orange. And just because this is a little tedious calculation, and not so tedious, but you know, there's a lot of details going into this. We have 1 minus s to the p. 1 minus p. This whole thing is 1 minus x. Now focusing on this business inside the parentheses, you can just multiply in the 1 minus p. We have then 1 minus p, and then we have plus 1 minus p, and we have 1 minus s to the p. We have 1 minus p minus x, but these things cancel here, and so we end up with 1 minus p plus, we're going to multiply in the p, plus p minus sp, right? And this whole thing becomes just 1 minus sp. And look at this. Look at this. This is just now basically ending up. We've proven that this term, I'm going to write this thing here. We have the n minus x and minus x. Don't forget that. Up here, 1 minus sp and minus x. We've proven in fact that this thing becomes this binomial business here. There was a lot of calculation involved. I mean, you know, it is in fact much easier to do the story proof, but it's I think it was nice to just, you know, go through this whole calculation and see that it actually reduces down to this binomial. And yeah, this is it. So we have proven how the marginal of x is a PMF that is binomial in two ways.